Okay, this is the Professor, CBMD PhD, and today's Tuesday, August 22nd, 1923. It is 3:33 and 18 seconds, AM Eastern Standard Time, and today's research, mathematical modeling in cancer. So let's hop to it here. Researchers use mathematical modeling and dynamic biomarkers to characterize metastatic disease during adaptive therapy. Metastatic tumor characteristics and heterogeneity influence therapy responses. Date August 15, 2023. Source: Ainsley, Moffitt Cancer Center and Research Institute. Metastatic tumors can vary in size, location, and composition. Metastasis also vary within the individual patient, making treatment decisions challenging. Physicians use biomarkers collected from blood specimens, tissue biopsies, and images to identify appropriate treatment strategies. However, these techniques are limited by single time points, poor resolution to smaller lesions, and an inability to provide information on individual metastases. Scientists are investigating the potential of dynamic biomarkers to overcome the limitations of standard biomarker approaches. As dynamic markers base prognosis not on the absolute value of measurement at a single time point, but on the relative change over time. For example, prostate-specific antigen doubling time may stratify patients with prostate cancer who are likely to respond better to chemotherapy, progress to metastatic disease, or die from the disease. They focus their analysis on a biomarker called prostate-specific antigen that is commonly used in the diagnosis and treatment of patients with prostate cancer. The researchers performed their study with data from 16 patients treated in a clinical trial of adaptive therapy. During adaptive therapy, patients are given breaks from treatment based on their change in prostate-specific antigen levels. This approach is designed to prevent the development and growth of drug-resistant tumors that cause treatment failure. The researchers assessed dynamic prostate-specific antigen biomarkers during the first cycle of adaptive therapy, which includes the time it takes to reduce the prostate-specific antigen burden by 50% when treatment is on, and the time it takes to regrow to the original value when the treatment is off. They identified several key relationships between metastatic disease and the biomarkers, including metastases that were larger in size, had longer treatment cycles. Metastasis with a higher proportion of drug-resistant cells slowed the cycle, and metastasis that had a faster cell turnover rate had a faster drug response time and a slower time to regrow. They also relate prostate-specific antigen dynamics to clinical variables, including Gleason score, a grading system used to show how abnormal the problem cancer cells look and how likely the cancer will advance. The change in the number of metastases during a cycle and the total number of cycles over the course of treatment. The team performed additional modeling to compare adaptive therapy to continuous therapy, during which no treatment breaks are given. They discovered that differences between metastatic tumor compositions favored continuous treatment, and differences within metastatic tumor compositions favored adaptive schedules. These observations suggest that it may be possible to use mathematical modeling approaches combined with dynamic and standard biomarkers to improve the characterization of patients' disease and help identify appropriate treatment options. Multi-scale mathematical models, such as the one proposed here, can help disentangle the multidimensional nature of cancer and lead to a better understanding of the drivers of treatment success and failure. While this work is only a first step, it shows that model-informed analysis of biomarkers and visible metastasis during a single cycle of adaptive therapy may be useful in identifying important features of the metastatic population to provide further support for treatment decision making. And this is the Professor Professor of Microbiology, Bioinformatics, Pathophysiology, and Nature of Research. This video was created for educational purposes only. Hope you enjoyed listening. Until next time, have a great day.